Okay, yeah. So we are very excited to have Zhongtian from Princeton. He is being advised by Mark Braverman, and he's interested in information theory. And today we'll be hearing about algorithms for match flow. Right. Okay.
Yeah, thanks, Sonia. So, yeah, I'm very happy to be here to give a talk on my recent work on Cactus representations in polylogarithmic max flow via maximal isolating Mincuts. So this is a joint work with Dashbon Sarnoa and Sean Fong. So let me remind you the basic definition of a Mincut. So we are given a weighted undirected graph G, and the problem is you want to find its Mincut. So a Mincut is a partition of the vertex set such that the boundary is like minimal. And know that so this is a simple version if the graph is unweighted, and in general you can have weight on the edges so that the cut is defined by the minimum of the total weight of the edges. And there is a basic theorem says that there are at most quadratic number of Mincuts on the graph. So if you want to find all the Mincuts, naively you need to it takes cubic time and space. Because like for each Mincut, you can use a subset of vertices like A to represent it. And if you want to list all the Mincuts, then it takes cubic time. For example, you can think about the graph like a cycle, right? It has a quadratic number of Mincuts. And now, like the question is whether we can do it more efficiently in terms of like space or time complexity. Unfortunately, the answer is yes. There exists a data structure called Cactus representation. And let me tell you what a cactus is. A cactus is a graph where every edge participates in at most one simple cycle. So for example, this graph is a cactus. Okay, so and there's a theorem by Diniz et al. At 76 says that for any graph G, there exists a linear sized cactus graph that preserves all the Mincuts of the given graph. For example, in this graph, this G, the Mincut of this graph is 2. And there exists a cactus graph H along with a mapping from the vertex set in G to the vertex set in H, such that for any Mincut in G, there like if you map if you use this phi to map all the vertices on one side to the vertices in H, it also corresponding to the Mincut, and vice versa. So there's like one-to-one correspondence, and also note that this phi might not be surjective or injective. So there might be node that there are multiple vertices in G mapped to the same node in H, and also there might be an empty node that no vertices in G map to it.
If the new graph is in the Mincut one, I guess
Okay. I should say like this edge, the bold black edge is has weight 2, and this simple edge like has weight 1. So so it's always like in the cactus, the edge in participating in a cycle has like weight lambda over 2, where lambda is the Mincut of G. And the edges, we call this maybe tree edge, has a weight lambda. So it preserves the Mincut. So yeah, Eric.
Are all the sets disjoint? Like all the H's, the representation of H's, like every vertex in H corresponds to a set vertices in G.
Yeah.
Is that always a partition?
Yes. Cause like phi is a map. So yeah. Yeah, any more question on the definition? All right, so yeah, let's see some more example of the Mincut. Okay, so as an algorithm person, like we care about the fast algorithms. So there exists a Monte Carlo randomized algorithm by Carter and Panigrahi in 2009. that compute this Cactus graph in near linear time. And in our recent work, we de-randomize this algorithm and improve the complexity in the randomized case. So this particularly round one this paper is the best paper sold out this year. This gives the first deterministic time algorithm to compute a near linear time deterministic algorithm to compute a single mincut. But this is not enough to compute all mincuts, the Cactus representation. And it turns out that there are additional random step in KP09, like this paper, that in our work, we de-randomize this step to make all the things deterministic. Yeah.
Sorry, by preserving mincuts, you mean if each mincut where you can add new min or under mincuts? Yeah, exactly.
Exactly the same. So yeah, so this is a good question. So can verify that any mincut in H corresponding to any mincut in G and vice versa. So all right, and so we won't have time to present this result. In this talk, we will focus on this Steiner version. So we are given a proper set, subset of the vertices, T, and we want to find a proper subset X so that the cost to disconnect X from T minus X is minimized. So this is a generalization of global mincut, because you can just set T to be V, right? And it is also a generalization of ST mincut, because you can just set T to be the set S and T.
What is T?
T is a terminal set, is a subset of vertices. So you want to find the minimum cut that disconnected T. So for example, in this graph, if we set T to be those 5 red vertices, and 6 and this guy, the Steiner mincut will be 2. And there is a theorem says that there exists a linear sized Cactus graph, linear with the size of the terminal, such that it preserves all the T mincuts. So in this case, there exists this Cactus graph, and it preserves all the Steiner mincut, like the singleton G and this one and so on and so forth. So preserves all the mincut. And note that we only care about the mincut, the partition of G that forms a mincut. So if this graph looks like this, and T to be those 2 vertices, there might be many Steiner mincuts in between. The information we want to preserve is that whether for each partition T, like A and T minus A, we want to preserve the information that whether there exists Steiner mincuts that partition T as A and T minus A. So if the graph looks like this, the Cactus will just be this single edge. So this is a clarification. So any question about the definition of Steiner Cactus? All right, so yeah, let's see some more example maybe. This in this case, T is this set of 3 vertices, and the Steiner mincut is 3. So the Steiner mincut might be different from the global mincut. So you need to delete at least 3 edges to disconnect it. Okay. And now that comes to the algorithm part. Dinitz and Weinstein show that you can use T max flow call to compute the Steiner Cactus. And Cole and Hariharan, they gave an algorithm for the simple graph. So this lambda is a like it's a value of the Steiner mincut. So if the lambda is small, then the algorithm runs pretty fast. But in general, the algorithm is slow. And our work is that we use polylogarithmic max flow calls to solve the problem. And since like now max flow is almost linear time, so the whole algorithm runs in almost a linear time.
Here you're assuming something like M is more than T, right? Because you'll need like T times at least write down the whole thing.
Sorry?
So this bound is independent of T. Okay, the size of
Oh yeah. Because T, the set of T is T is a subset of vertices. Yeah.
Yeah, so M is more than N.
Yeah.
So M-
Yeah, we can assume the graph is connected, and so yeah.
So the colon error.
Mhm.
That algorithm runs without doing any max flow computations.
That's a good question. Yeah, sorry, I don't know, but it's a very good question. All right, so, and one more generalization is the hypercactus representation for the hypergraph Mincuts. So we won't have time to talk about this in this talk, but like this is for like for the result. For any hypergraph, there exists a linear sized hypercactus graph that preserves all the Mincuts. So for example, in this graph, the Mincut is 2. Then you can remove those 2 hyperedges to disconnect the graph. And you can have a hypercactus representation. Yeah, but the definition is a bit tedious, so I will just skip this part. So but our algorithm also works for hypergraph setting.
So why didn't he hypercactus? Cactus graph was already capturing the Mincut.
So in hypergraph, so let's use this example. So let's see this Mincut. This Mincut corresponding to removing those 2 hyperedges, right? Those 2 gray hyperedges, and this Mincut disconnected the graph into several parts, like this part, and this part, 4 parts. And this hypercactus could capture this. Like yeah, and also I don't think there exists let's see.
I think I misunderstood. So this is for hypergraph.
Yeah, this is for hypergraph. Yeah. Okay.
All right.
Okay, thanks for your questions. And I think this is all the results part. And in this talk, we will focus on the normal graph and the standard version.
What is P?
Oh yeah, so P is the total volume of the hypergraph. Say the input size of the hypergraph, we call it P. Like P, the summation of the volume of all the edges, hyperedge. Yeah, basically all the things runs in almost the linear time with the size of the input.
So the input in this case is a set system, right?
Yeah. The input of a hypergraph is of size linear to P, right? So P is the summation of the rank of the edges. So right. Yeah.
I might have missed the previous slide. So for hypergraph, do you somehow compute with Maximal or it's completely different?
We use Maximal. Yeah, because like in the result, we use.
Okay.
Yeah, sorry, like I skipped this part. Yeah. All right. Sorry. Okay, so this is the outline of the algorithm. We will follow the divide and conquer framework based on the previous work by Cactus and Xu. And then we will introduce a very powerful technique called isolating Mincuts. And we'll show that this technique is not enough to solve our problem. And we'll give a new variant of this isolating Mincuts. And we'll show how to compute it. So let's start with a contraction-based divide counter framework. The idea is each time you want to find a non-trivial T-mean cut and which splits the graph into two parts, and you contract each part and recurse, and you recover the Cactus representation from the sub-Cactus you build in the subgraph, in the subproblem. So let's see it one by one. So the first step is to find a T-split. A T-split is defined to be the partition such that both sides contain at least two terminal vertices.
How do you define terminal?
Oh, terminal is a set T. So it is the input, say the red vertices. All right, so here you want to find some non-trivial T mean cut. So you want to find some standard mean cut basically. And after doing that, and you want each set has at least two terminal vertices because you want to make progress. Because you want, after contracting each side, you want to make progress. So actually, I lied a little bit. So these two terminal vertices follows from the. Okay, I need to mention that we need to do a pre-processing step that you contract all the lambda components, lambda connected component. Because I say initially, like if two vertices are not separated by any standard mean cuts, you can just contract them. Okay, so you can just contract L and N. So now like contain at least two terminal vertices, you count this as one and this as the other. And this cut will guarantee you to make progress. Because when you contract one side, the total the size of T will decrease. Right. So this guarantees progress, and then you do both sides. And finally you recover it from the subcacti. How you do it is just by testing that whether you should glue them as a larger cycle or you just glue them by an edge. So there are different cases, but you just believe me, you can do it by Maximal call, right? To distinguish the cut structure locally. Right? And
Subcacti is the Cactus of the contracted version.
Sorry?
The subcacti.
Oh, the
Is that
subcacti.
the Cactus?
Yeah.
The contracted set?
Yeah, so these are the subcacti. So they corresponding to the subproblem. Yeah. All right, so yeah, and last thing to mention is the base case. So in the base case, the Cactus is either a triangle or a star. In this case, you cannot find any non-trivial T-mean cut because there are no T-splits anymore. So at all. So and you can use like Maxwell call to distinguish these two cases. All right, this is a framework, but it's not efficient, right? So if you find arbitrary T mean cut, then it doesn't guarantee to have like polylog depths for the divide and conquer. And what the previous work do is just find some arbitrary T-splits using the Maxwell. And here we want to bound the depths. In a sense that we want to find some balanced T-splits. Okay. So this is our goal. So just keep it in mind, and I will take a detour to tell you a very powerful tool called isolating Mincuts. So this will be the second section. So this tool is very simple and very powerful. It has been used in many papers in recent years. Like it solves the Gomery-Hu tree and related like cut-related problems. But it will not be useful for us. Like and you will see. So we will introduce a new variant, but the definition in this part is useful. And we are based on it. So let's go to the definition. Given a set of terminals, for each terminal X, we want to find the minimum value cut that separates X from the rest of the terminal. So this is a definition of isolating mean cuts, as the name suggests. And we can also call it X mean cut of T for gravity. So, and what the previous work did is is finding a minimal isolated mean cuts. Here, the minimal means like this. So suppose like this is a mean cut of x. This blue line describes the mean cut. And we can use a subset containing x, this part, one side of the cut, to represent this mean cut. And the minimal means like this, the size of this part is minimal. So for any forward subset, it has a strictly larger cut value. So like this. And with respect to the size of the
The larger here is just in terms of the size. There are no weights.
Wait, the boundary.
Oh yeah. Sorry. So larger cut boundary. So this is a summation of the weight of this on the cut. Yeah. So this is a definition, and it turns out like there should be at most one minimal isolating mean cut. Say yeah. So this is by submodularity, because if you have two subset x and y, suppose they intersect, one not containing in the other, then you can just take the intersection and cause like they are mean cut, so all of these values should be the same, and you get a minimal one eventually. So the uniqueness comes from this, and the previous work says that given any terminal set T, there is an algorithm that computes minimal isolating cuts for every terminal in T using polylog max flow call. So naively, you can compute it by T max flow call, right? So you just pick every terminal and you contract the other terminal and use a ST max flow to compute the mean cut. But the interesting part here is that you can use polylog max flow. So we will see how to do it. And before showing the algorithm, let me just introduce some more definitions. So previously we defined X mean cut of T, and we can generalize this definition to A mean cut of T, where it is a subset of terminal. And A mean cut of T is minimal, defined the same way as a minimal isolated mean cut. So this is a minimal one respect to the size of the part containing A. So a formal definition is here. So X should be a cut of A. It contains A and it disjoint from T max A. And the weight of the cut is minimized. And based on the previous two, the size of this part is also minimized. So this is a mean cut of T. So anyone have any questions? So
A is just an arbitrary subset of terminals?
yes, it could be any subset of terminals. Yeah. So just let me emphasize that from now on we shall just say use a set of vertices to represent the mean cut. Okay. Yeah. So suppose we arbitrarily partition T into two halves. We can compute the minimal A mean cut of T and minimal B mean cut of T. And by submodularity, we can show that minimal X mean cut is contained in minimal A mean cut. So this is so the intuition is exactly the same as the uniqueness of the isolating cuts. Because like if this blue thing overlap with intersect with this red mean cut, like the blue mean cut is not contained in the red, then you can just take the intersection, which is also a X mean cut.
Just clarify, it can intersect, the two lines can intersect, right?
Oh yeah, they can intersect. By intersect, I mean the subset of vertices.
Right.
Yeah. So if
Oh,
the
I see.
subset of vertices containing X is not contained in the subset of
Oh, yeah.
vertices containing
Okay,
A,
okay.
then you can just take the intersection.
Yeah, then you can, then.
Because like this is the union is a A mean cut and the intersection is X mean cut. So by this you can prove. And based on this, we can yeah, this will lead to a divide and conquer algorithm for isolating Mincuts, because we can contract and recurse, and it preserves all the isolating Mincuts for A side and for also for B side. Yeah. So the algorithm is really simple.
So go back for a second.
Yeah.
So when you talk about an A Mincut, it is not necessarily a global Mincut. Is that right?
Yeah, not necessary, and not necessarily a standard Mincut as well. Right.
It's not.
It is not. It's even not necessary that A Mincut is a standard Mincut. Yeah.
Okay.
Yeah. So isolating Mincuts may not be standard Mincut. Yeah. So.
Then I'm a little bit confused because in the end, you want to separate the blue, the purple vertices from the orange vertices. And then it is not even a standard cut. Oh, because the cut could be inside this also. I see.
Yeah. So in this subroutine, what we care is isolating Mincut. So you want to separate each terminal with the rest of terminals. Yeah. So the connectivity locally might be very good. Like this vertex could connect to everyone. So, but we will see like how to use this tool to compute standard Mincut in the next stage. Yeah. It just make sure everyone like fine with this definition.
And by the way, so far I don't see why this thing is very efficient, because even you recurse, you have to the size reduce drastically.
Yeah, like I should say those two things doesn't overlap. Sorry.
So you do not do like polylogarithmic, like
yeah. I cheated. I lied.
right?
Yeah, I lied a little bit. That
Yeah.
Good catch. So
Yeah.
So the total volume of the Maxwell call is polylogarithmic
Yeah.
times the
Yeah.
total size.
Okay.
Yeah.
Yeah.
Cool. So now I will answer your question that to show how to use this to compute the standard Mincut. Recall that the standard Mincut is this. So we are given a terminal set T, and you want to find a partition that has a minimum possible value cut among all the non-trivial partition of it. Okay, so let's let's just start from scratch, like to see what kinds of algorithm could we get. That observation is that for a standard Mincut, if we fix any terminal A, then the standard Mincut must separate A from some terminal B. Right? So then this leads to a algorithm using T Maxwell calls that you fix the vertex A, you enumerate all the vertex B, and you make a Maxwell call and take the minimum one. And we will show how to use polylog Maxwell calls via isolating cut. So let's first consider an easy case. If the standard Mincut separates some terminals with all the other terminals, what shall we do? Yeah, just to run the isolating cut. Yeah, because this is one of the isolating cuts. Yeah. And what in general what if the standard Mincut has size say between this region? Would anyone suggest some idea?
It's not immediately clear how to take this information into the isolating cut steps.
Yeah, but it turns out that yes. Yeah, exactly. Yeah. So we sample a subset of terminals. As long as there exists exactly one terminal that's in this standard, then we are good. So then we just call. So, but we don't know how large is this intersection part, but we can guess. We can just repeatedly repeated logarithm. Yeah. So
But you don't, I see, I see.
yeah, this is a full algorithm. It's pretty simple. Yeah, first we guess the size of this S star intersect T, which is the blue, how many terminals the blue region contains. And we repeat log n times to boost the probability that we success. Each time we sample a T prime, and if there exists one terminal in one side of this standard mincut, then the isolating mincuts will just give us a value of standard mincuts. All right.
Kind of lost track. What is this algorithm solve? Which of this?
So now we are saying we want to use isolating mincuts to solve the standard mincut problem. Yeah. Yeah. So do you agree that this algorithm solves the standard mincut? All right. So now we know how to compute the standard mincuts. Let's get back to the standard Cactus, which solves all the standard mincut, right? So which is a strictly harder problem. And to compute that, it turns out that we need to introduce new variants of the previous technique. We say the X mincut of T is maximal if all proper superset containing X has strictly larger value. And our work says that we have an algorithm that computes the maximal isolating mincuts using polylog Maxwell calls. And it might be a bit confusing now that, because like I haven't shown you like if we can even store all the maximal isolating mincut, right? They might overlap. Like it's not like a minimal one. The minimal one, they don't overlap. Yeah, just by, yeah. And we'll see like how to compute it and how it will be useful.
But will you show us why the minimal, the whole idea doesn't work for the Cactus?
Yeah, I will show you in the
Okay.
next, yeah, why we need this. Yeah. So let's consider some simple cases. If the input graph is a complete graph and with those red vertices as terminals, then the Cactus is a star. So those 4 red vertices are mapped to the leaves of this Cactus, and this is an empty node. There are no terminals mapped to this. Okay. And and if the graph is a cycle, and in this case the Cactus is also a cycle.
Right.
So let's see, like if we let's try to use the minimal isolating mincuts to compute it, to see what cuts we can get. But it turns out like regardless how you sample the terminals, the minimal isolating mincuts will always return the singleton in both cases. So that means you cannot distinguish them naively. But if we introduce this maximal isolating mincuts, it turns out like it will return some non-trivial mincut if we do the subsampling, right? In the cycle case, it will return some more balanced cut, which is what we want. Yeah, because that we want to recover some balanced standard mincut, which makes the divide and conquer more efficient. So this is the intuition of why we need maximal isolating mincuts. Yeah.
Repeat this thing again.
Yeah, sure. So first we want to try to use the idea that solves the standard mincuts problem to solve this problem. But it turns out like though this minimal isolating mincuts would return some standard mincuts like this, all these are standard mincuts. That's fine. But the problem is that there are some cases that this minimal isolated mean cuts cannot distinguish, like this cycle and star cases. Because like regardless how you sample the terminals, the orange terminals are the terminals you sample, and the minimal isolated mean cuts will always return singleton. Say always return some trivial cut. It just doesn't provide any useful information. So this is an intuition. I'm not saying that you actually. I'm not saying that it's actually impossible to solve it by minimal isolated mean cuts, but we faced some barrier there. So that's why we introduced a new variant. Yeah. Because like in this maximal isolated mean cuts, if you first do a subsampling, and then you compute the maximal isolated mean cut, it will return this red cut, which is the cut we want. Right? We want to find some balanced cuts to make the debug counter more efficient. Yeah. Okay, so let's now formally introduce the algorithm. So given the graph, let's consider the underlying Cactus representation, which we don't know now, but there are two cases. So one case is that there exists a balanced edge cut in the current Cactus. That a balanced, I mean, both sides contain at least a quarter number of terminals. So for example, this the two blue parts both contains at least a quarter terminals, quarter fraction. And in this case, I will show you like how to compute a balanced standard mean cut. But like it turns out there exists a case that there actually doesn't exist any balanced standard mean cut. Consider the underlying Cactus presentation looks like something similar to a star. Basically, I'm saying there exists a centroid, right? So in this case, like every standard mean cuts are not balanced. But we are still fine with this, because like I will show you how to use the maximal isolated mean cuts to compute a lot of cuts in one shot, and then like each of these blue parts will be recovered by this by the cuts we computed. So then we can do divide and conquer for each branch. Okay.
So this conclusion, you said, if there's no balanced edge cut, then there exists a centroid. And a centroid is a node which, if you
delete it, then like every part is small.
I see.
How small is
And-
small?
So by this assumption is every part is less than T/4.
Constant fraction is fun.
Yeah. I think the key here is that our maximal isolating cuts can recover all the blue parts at the same time by polylog Maxwell cuts. So this is the observation. So let's first do the easy case. If there exists a balance, what shall we do? Is that we can just sample three nodes, three vertices. Sorry, three terminals. And if one terminal lies in this part, we don't know where this part is, but we can repeatedly do many samples that with constant probability, one terminal lies in this part and two lies in this part.
Okay.
And if you look into this case, like what is the maximal R mean cut? It will be this orange mean cut. And by the proposition of the DFS tree, that the remaining part is at least T/4 with constant probability. So this might be a bit confusing, but the intuition here is that, okay, let's first fix R here, and if you uniformly sample two vertices in the right part, then a mean cut maximal any min cut of R will have so let's consider a simpler case that the cactus is a tree. Okay. So in this case, let's see the furthest node from R that on the path to both U and V. Then the cut cannot cut anything after this node. Sure. Then I would say okay, let's call it root. That's why I should say that. So this will be the LCA of this common ancestor of U and V. And and the claim is the size of the subtree of this node is at least T/4. Yeah, might be. It's,
Let me ask you this. So I think the confusion here is that because you said the balance net is between these two blue parts.
yeah.
And now you're
Yeah.
saying that.
So this is
after-
how we prove this. So we assume there exists a balanced edge cut, but like the actual min cut that the algorithm returns may not be this blue.
Yeah.
min cut.
So
Yeah.
this is not the balanced isolated cut. This is like balanced edge cut.
Balanced edge cut on H, and it is also a Steiner min cut for RUV, but our algorithm is not guaranteed to find this cut, but I say that it is guaranteed to find some balanced cut. Okay.
Yeah, so can you give an intuition on that? I mean, why couldn't it be that these maximal cuts always,
Like separate,
you know,
it's
just
like-
have just
Yeah.
a small part left?
yeah. So I don't know if it is good to tell the proof in detail, but like the proof is like you fix this R, and you consider the pre-order traversal, the pre-order of all the vertices, and if like say that you sample U and V, and you see their pre-order, and the vertices in between will always be on
The
this,
other side.
yeah, some DFS property. Yeah. So just to remind you that these graphs are Cactus graph. The underlying Cactus graph is not the original graph. Yeah. So we based on the fact that there exists an underlying Cactus graph. Okay, so this is the easier part, and the hard part is this, like we want to obtain a set of cuts corresponding to the blue one. Okay, so for each TI, where TI is one of the blue part, we consider sampling each terminal with probability 2 to the minus log TI. Then with constant probability, exactly one terminal in TI is sampled, together with at least one terminal from any two other subsets being sampled. So this is like a very
Okay.
yeah, weird thing, but like as the figure shows, like in this case, when you do the maximal isolated min cut for W, it will recover this, because at least one terminals from two other set got sampled, so you cannot cut anything beyond the centroid, right? You can only cut this branch, and it will gives you TI. So we use this trick that we adjust the sampling rate. We enumerate all the log and possible sampling rate, and it's guaranteed that we can get all the blue sets. All right, so both challenges are solved. Just remind you the goal that we want to bound the depths of the divide and conquer, and if we can do that, the algorithm will be efficient.
Go back to the big slide. What is it exactly like in some of the subtrees, you might have more than one vertex sample. You're not aiming to have exactly one vertex each, you're just aiming for there to be 3 different ones that have exactly one vertex, or?
Not necessarily 3, that I just need that exactly one terminal in TI is sampled. And for the other part, at least one terminal from any 2 other subset being sampled. There can be more. So if TI is small, say TI is 2, then I just sample each terminal with probability a half. Then with constant probability, one of the terminal in TI will be sampled. Yeah, and there might be many terminals in the other part being sampled. But if we compute the maximal isolated Mincuts, it will recover TI, because if exactly one of the terminals in TI got sampled, then it will return the subset. Okay, so that's all the divide and conquer algorithms. And have you done? Not yet. So I haven't tell you how to compute the maximal isolated Mincuts. So so this is based on the pairwise intersection only lemma, which is called 3-star lemma. So we basically rediscover a theorem in '94 by Dennis and Bernstein. Says that given 3 disjoint sets of terminals, A, B, and C, then the intersection of any A Mincut, any B Mincut, and any C Mincut is empty. So the reason is by positive modularity of cut value. Since the Cx plus Cy is larger or equal to Cx minus y plus Cy minus x. Yeah, so yeah, so I think I won't have time to tell you the proof of this theorem, but intuitively it throws out the case that there are intersection here, because we can so we can just count the contribution of some edge from here to here. For example, you can prove by contradiction that there exists some edge from the intersection part to somewhere else. Then it will violate the okay, the proof looks like this. So you consider A minus C and A minus B, that this part, which will also be a Mincut. And also this thing holds for B and this thing holds for C. And then you count the contribution of some edge from the middle to the to somewhere else.
That maybe the worst to tell first. How to relate to help us?
Yeah, that's a good point. So maybe let's just skip how why this theorem holds. But like how it helps us is like each vertex appears at most 2 maximal isolating Mincuts. So because like each isolating Mincut, so if you suppose by contradiction that some vertex appears in 3 maximal isolating Mincuts, then it will violate this theorem.
So that theorem holds even for any maximal or not.
Yeah, it holds for any. So then of course it holds for maximal. Yeah.
So I imagine that for the hypergraph, there is some similar theorems.
Yes. But like we need to
More sets.
we need to redefine the definition of A Mincuts in that case.
But it's again 3 sets.
Yes.
For hypergraphs also 3 sets.
Yes, there is an analog. Yeah, that's why the yeah still holds. So so this answers the first question, that why we can store all the maximal isolated Mincuts in linear size. And the second part is that how to compute it efficiently. And this actually follows from the same framework, divide and conquer framework. Again, by some modularity, we know that maximal x min cut is contained in maximal a min cut. And if x in A, and then we do contract and recurse. Say we compute the maximal a min cut, and we contract the other part and recurse A, and we do the same thing for B. Now they might overlap, right? When we do the recursion, the two parts might overlap, but we can bound the total volume of the the total volume on each depth of the recursion tree. Because on each depth, the subproblems are defined by a partition of the terminals, right? And now like each part is a maximal isolated min cut of that part. And by the pairwise intersectional lemma, each vertex in the original graph lies in at most two subproblems on each depth. So this tells you why this idea works, like the same framework. Okay, so any question for this part? Yeah, so that's all. In this talk, we just a quick recap. So we have solved the standard Cactus representation, which is log cube time randomized algorithm and near linear time deterministic algorithm. And for the Steiner and hypergraph Cactus representation, we do it in almost a linear time. And it remains open for element cut Cactus and general submodular functions. So by Flanner and Jordan's work in 1999, they show that for any submodular function, there exists this hypercactus representation for all the like minimum of this submodular function. And yeah, the same reason holds for element cut. Element cut means that you can delete both edges and vertices. Yeah, and those are Cactus, and beyond Cactus, there are problems like near min cuts. That there exists a polygon representation that preserves all the, say, 4/3 or like 6/5 near min cuts. In
dimension, what are these polygon representations?
yes, so in this case, we consider all the near min cuts like a constant approximate near min cut, like 6/5. And we want to preserve all such near min cuts. So there exists a polygon representation, which looks pretty similar to the Cactus, but now the vertex are mapped to the point on the plane. Okay, okay. So now the vertices are mapped to the point on the plane, and there are polygons, say like each diagonal, like and some diagonals, and each diagonal corresponds to a near min cut. And this polygon satisfies some properties. That is not arbitrary polygons correspond to
always convex.
Yes, and it's and there are additional constraints on it, like deformable. So that might be close to detail, but basically the structure looks like this. Some diagonals corresponding to near min cuts, and you can always map the vertex to the on the plane.
What happens if you are in the streaming model? If things are streaming, the graph
Streaming. Yeah, that's a good question. So Yeah, like I'm not that familiar with streaming.
You can compute a cost specifier during the stream and compute all of them in the end. I think that's no problem. Maybe.
Cool.
I think so, but I think if you want something that like some task that requires you to run this during the stream, then it's another story.
Yeah, that would be hard, I guess.
Not like during the stream.
I don't know, like I mean maybe for the zero robots or something, you need to query at each time. Yeah. And
Oh,
then
I
you want to be like, yeah, and then the adversary is going to see your output and going to insert the next edge. Some version like that, that sounds hard. But like if just one shot output in the end of the stream, I think you can run a cut multiplier and do things. Yeah. But on that, I think like so I think that at some point I saw something about this oscillating cut that doesn't work with approximate max flow, at least not trivially.
For approximate.
Yeah, well, 1 plus epsilon.
Yeah, I believe that like yeah. So there is an algorithm to compute this, but completely different from isolating mean.
Yeah, like I think, well, I think the trivial way you would think is to like compute the approximate flow, pick the cut, return for that, and then pretend it's actually a mean cut. I think there's some issue, but did you look into this before?
Sorry, I don't know how to compute it. Like but yeah, I believe that naively doing that might be hard. Yeah.
Yeah, I think but okay. Oh, thanks.
Yeah, I roughly remember Maya and Jason's paper. Their algorithm is deterministic. So for this maximal isolating cut, is there efficient randomization?
Yeah, like we believe it can be made deterministic. Yeah. So yeah, as Jason like they had a recent work on it, like make the Steiner mean cut deterministic, right?
I think that's in the past 2020 or 2021, like deterministic.
No, like recently they even make the Steiner mean cut deterministic. That's a harder problem. Right? I think it's a paper last year or this year. Like so and we believe we can even make this deterministic.
By maybe similar randomization techniques.
Yeah. But it's less interesting in the sense like, oh, we have already like
Yeah.
okay.
The algorithm makes sense, but people have different opinions.
Oh yeah.
And just for this maximal isolating class, do you observe like other applications? Because
Yeah, that's a very good question. Yeah.
I don't know if maximal was the best.
Yeah, that's a very good question. So yeah, we tried a bit like but we haven't found any problems like using these techniques. Yeah, it might be very interesting if it can be applied somewhere else.
Is there some detailed explanation about when we glue back to Zucati of the standard cutters? How do we decide whether we glue them back to a big cycle or just glue by a? Is there any?
Yes. So this is a good question. So yeah, let's do it. So when we glue to let's say to triangle. So this is the vertex. This is the terminal that being contracted in the, and this is also the terminal that corresponds to the other part. So we want to glue them, and we call this a B, an X1. So if they are cycle, so if the underlying cactus is A, B, X, Y, then the mean cut. So if you contract A and X and B and Y, respectively, you contract the top two, and then you contract the bottom two. Then you compute the SD mean cut between them. Then this should be a standard mean cut. And otherwise, if the underlying cactus is just you glue those two anchor vertex together, then this is not a standard Mincut. So you can distinguish it using Maximal.
So then that means in order to determine which case I need to be able to read the whole underlying graph into the memory. I need all the edges need to be in memory.
So sorry.
This means that I need to do this in the RAM. Means I cannot do this externally, semi-externally.
Yeah, I think all the things in this talk are just assumed like if you don't have memory restrictions. But also I think these things are efficient because every time you do the recursion, you don't create more than n edges at all. So it's like the same as you have your graph in the RAM.
Yeah.
Okay, let's